Hello and welcome to this question that we've got. So figure 8 shows a sketch of the curve C with equation y equals x to the power of x. Firstly, by taking logarithms, find the x coordinate of the turning point of C. So here we can't use any graphical or numerical methods, so we're going to have to go and use logs to do this. Now for this step here, we're going to use a little bit of a trick, and that is to convert x to the power of x into something that's more manageable. So to solve this one here, we go over to this part. So move over to this part of the board. So we've got y is equal to x to the power of x. And then from here, what we're going to do is we're going to manipulate this question, this part of the question here. So it's looking to get logs. Now, here what we can do is we can say the following, that sorry, no, not ex, ln x to the power of x is equal to x to the power of x. So the ln and e will cancel each other out, so you get back your original form x to the power of x. Now what does this allow us to do? Well, it allows us to then rewrite this ln x to the power of x is equal to e to the x ln x. So for this result here, we then get something that is more differentiable. So this is equal to y. So if we've got y equals x to the e to the power of x times ln x, the next step we do is we differentiate it using the chain rule. So we're going to take u as x ln x, and y is now equal to e to the u. And then we're going to differentiate this function x ln x. To do that one, we're going to use the product rule. So we use a is x, a prime is 1, and now b is ln x, and b prime is 1 over x. The product rule, if we remember, is y prime is u prime v plus v prime u. This time obviously we're not even differentiating with y, we're differentiating with u, but we can just replace in our values. So we get du dx is equal to 1 times ln x plus x times 1 over x, which simplifies to ln x plus 1. When we do this one, dy du will differentiate to e to the u. Okay, the standard result for an exponential. So from here, then we just say, well, dy dx is equal to du dx times dy du, and this is equal to e to the u times ln x plus 1, which is simply going to equal e to the x ln x times ln x plus 1. Now that's when we differentiate it. The reason why we differentiate it is because we're looking for a turning point. So we know for a turning point that dy dx is equal to 0, and therefore we can then solve it. So we say that 0 is equal to e to the x ln x times ln x plus 1. Now e to the x ln x, as we stated before, is simply equal to x to the power of x. So we can say that x to the power of x times ln x plus 1, and x to the power of x is equal to 0, or ln x plus 1 is equal to 0. This is our answer here. So ln x equals -1, and therefore x is equal to e to the power of -1, or equal to 1 over e, as your final answer for x. So this one was your answer to part A. So for part B, we've got here the point P, A2 lies on C, show that that A is between 1.5 and 1.6. This one is nice and easy. It's a bit of a trick question here. You just need to show, so therefore this is a very simple equation. All we've got here is y equals x to the power of x, and then we just sub in some values. So we know that x is equal to 1.5. So we're going to say that y is equal to 1.5 to the power of 1.5, and that gives us a result of 1.837. And then x is 1.6, so y is 1.6 to the power of 1.6, which is equal to 2.121. So that is part B. And then part C, we use an iteration formula that they've given to us already. So again, this one is not too difficult once you crack what you need to do. So here we're given the formula that the next term, xn plus 1, is equal to 2 times the current term 1 minus to the power of 1 minus the current term. So it gives us the first term, x1 is 1.5, so therefore x2 is equal to 2 times 1.5, 1 minus 1.5, and we're going to go all the way to x to the power of 4. So if you plug this into your calculator, you will get a result of 1.63299. Obviously, it doesn't really matter. The more decimal, to be honest with these questions, you should just put your answer straight in. So on your calculator, you should put 2 answer 1 minus answer like that, and that gives you the most accurate result. But as long as you take more than the decimal places or significant figures you need, you should still get the correct answer. But the answer button is your best friend here. So x3, the third value here is 1.46627, and then for the last one, x to the power of 4, we are going to get 2 times 1.46627, 1 minus 1.46627, and this gives us 1.67313. This is where we're up to, so essentially 3 decimal places, 1.673 should be your answer here. And then part D looks at the long-term behaviour of x to the power n. If you're not sure here, then do continue and just keep plugging in values and seeing what you're getting. So x to the power of 5, if you plug it in, I've done this one already, gives you an example of 1.4144. So if you look at what's happening here, is that you will have a function. So you've got 1.5 as your starting point, so x0, then x2 is 1.63, then x3 is 1.46, and then so this is x0, x1, x2, and then x3 is this is x1, this is x2, and this is x3, and then x4 is 1.673. Well, that's bigger than this one, so that's actually moving away. So x4 here and 1.4144 is actually further away. So what's happening is you are getting a diverging series, okay, because the values are getting further and further away as you get a bigger x, as x to the power of xn increases. Okay, so this is a diverging iteration formula. You will not find what your value is using this one. Okay, so that's the first question that was sent. The second question is going to be a log question. Let me import it in. Okay, so we've got 3 questions here all about logs. So for question 6, we have the following. The amount of an antibiotic, y milligrams, in a patient's blood screen T hours after the antibiotic was first given is modelled by the equation y equals ab to the power of t, where a and b are constants. Show that the equation can be written in the form log base 10y equals t log base 10b plus c, expressing c in terms of a. So for this one is essentially, you start off with your equation. So 6a, y equals ab to the power of t. Then we take logs of both sides. So we take log base 10y equals log base 10ab to the power of t. Then using your log rule, log base 10a plus log base 10b is equal to log base 10ab. Here we're going to split up the right-hand side. So we end up with log base 10y is log base 10a plus log base 10b to the power of t. And then here we can do a little bit of rearranging. So log base 10y is equal to log base 10a plus t log base 10b. And then from here we've got log base 10a, which we can, if we look at our equation, that is essentially, we've got log base 10y, we've got log t log base 10b, but we're missing our c, which is just equivalent to log base 10a. So c is equal to log base 10 of a, so therefore log base 10 of y is equal to c plus t log base 10b. And there we go, collect your marks. So that's part A. Then the next step we've got is a doctor measures the amount of antibiotic in the patient's bloodstream at regular intervals for the first 5 hours after the antibiotic was first given. She plots a graph of log base 10y against t and finds the points on the graph lie close to a straight line, passing through the point 0, 2.23 and with a gradient of minus 0.076. Estimate the value of A and B. To two significant figures. So for this one, we've got a graph of a log base 10y on the y-axis and t on the x-axis. And we're given that it crosses at 0, 2.23, and that it's got a negative gradient. So it goes something like this. So what can we find from here? Well, essentially, we use this equation here, log base 10y equals c plus t log base 10b. We know that a straight line is in the form of mx plus c. So we know that c is the y-intercept, so c is log base 10a. Here, the y-intercept is 2.23, so we say that 2.23 is equal to log base 10a. So therefore, we just say that 10 to the power of 2.23 is equal to a. And therefore, a will be given as 169.82, which you want it to two significant figures, so therefore A is 170. And then the second one we've got is the value for B. Well, here, if we look at our graph, t log base 10b, we've got t is your x value, so t is the x-axis, so therefore log base 10b must equal the gradient. The gradient in the question is given as minus 0.076. So we say minus 0.076 is equal to log base 10b. So therefore 10 to the power of minus 0.076 is equal to b. From here, then we just plug that into the calculator. That should give a value of 0.84, which is equal to b. I'm just going to check that on the calculator, but I believe that is the correct value for it. Yes, 0.84. So that's your answer to part B. So we get our value for A and B, and then give a practical interpretation of the value of the constant A. So A is the, essentially A is when t equals 0. So when t equals 0, A is 170. Well, this means that remember the y value tells you, the y-axis tells you how much the amount of antibiotic in milligrams. So for this one, you need to actually read the question and then determine what it is saying. So here we're going to say the following: A is the initial amount of antibiotic given to the patient. Okay, so they're given 170 milligrams, so it's 170 milligrams, something like that will, it will suffice. And then CII, so in this one here, it tells you give a practical interpretation of the value of the constant B. So B tells you the rate of change of the antibiotic with time. Okay, so remember it's the gradient. So B gives you the change in antibiotic levels with time. Okay, and that finds your value here for this one. So therefore, or per hour. In fact, you should be a bit more balanced. So for change in antibiotic per hour, it should be, because it's per gradient. So time is in hours, so it should be in per hour if you want to be more precise. And then part D, use the model to estimate the time taken from the time taken after the antibiotic was first given for the amount of antibiotic in the patient's bloodstream to fall to 30 milligrams. Give your answer in hours, correct to 1 decimal place. So here we've got y equals AB to the power t. So for here we know that y is equal to 30. We've also given that A is 170 and B is 0.84. So we can use this value here. So 30 is equal to 170 times 0.84 to the power of t. And then from here we just rearrange. So 30 over 170 is equal to 0.84 to the power t. And then we're going to do log base 0.84, 30 over 170 to get our answer T, and T should come out at about 9.9 hours. So that gives you your 1, and then in question C, comment on the reliability. Well, the key thing here is to read the question and see what it says. Here it tells you that the model was for 5 hours, so 9.9 hours is greater than 5 hours, therefore the model is not reliable. And we can't use it for this one. So that gives you part E. So let's have a look at the next question then. So question 3 of what we're given. Okay, so the next question then is, we are given a setup here. Red squirrels were introduced into a large wood in Northumberland on the June the 1st, 1996. Scientists found that over time, the number of red squirrels can be modelled by the formula P equals AB to the power T. The line shows in figure 1 illustrates the linear relationship between log base 10p and t over a period of 20 years. Use this information, find an equation for L. So what it wants to do is, again, we're just going to use a similar setup to what we previously did. So we're given that P is equal to ABT. So this is the original model, but it wants us to find an equation for the line. So we're going to have to use log base 10. So we're going to do log base 10 on both sides. So log base 10p equals log base 10 AB to the power t. And then from here, we just do the same step that we've just done. So log base 10p equals log base 10a plus log base 10b to the power t. So therefore, log base 10p equals t log base 10b plus log base 10 of a. So that gives you part A. The line, so find an equation for L, find the initial number of red squirrels that were introduced into the wood. So here we have that the initial squirrels is going to be the following. So when log base 10p, so we're given here that the number of squirrels in the wood is p, so log base 10p is essentially equal to y, which is equal to 2. So here p is simply just going to equal 10 to the power of 2, which is equal to 100, because this is where t equals 0. So when t equals 0, you find that the initial value of on the graph, it's log base 10p. We want to find p, so we just have to rearrange this formula. So log base 10p equals 2, so p equals 10 squared, which is 100. Find and complete an equation for the model giving the value of b to 4 significant figures. So this is part B. So for part C, we now know that when t equals 0, log base 10p is equal to log base 10a. So 2 is equal to log base 10a. So we know that from just using basic line equations here. So the next step that we've got is we need to find the value of b. So for this one, we're going to use our equation and we're going to interpret some values. So log base 10p is equal to t log base 10b plus 2. Now we can replace log base 10a with 2, and then we're going to use that log base 10p is equal to 2.4 and t is equal to 20. So here we just end up as the following: 2.4 is equal to 20 log base 10b plus 2. And then we rearrange, so we move the 2 over, so that becomes 0.4 equals 20 log base 10b. And then we just rearrange 0.4 over 20 equals log base 10b. So 10 is equal to 0.4 over 20. And then from here we just solve. So 10 to the power of 0.4 divided by 20 is equal to 1.047. How many does he want it to? He wants it to 4 significant figures, so 1.047 is the final answer. So that is your answer to B. So that gives you the gradient. Okay, so this is equal to B. And then the next step then is it asks for the following. So we've got on June the 1st, 2019, there were to be 198 red squirrels in the wood. Uses information to show that the model is not valid on the 1st of June 2019. So we need to read the question carefully. And it tells us, first of all, that T is for the number of years. So first of all, we need to find, so we put this one DI up here. So first of all, find what this is. So we want to so we're in 2019 and we subtract 1996 away. So that tells us how many years have passed. 1996. So that tells us that 23 years have passed. Okay, so T is equal to 23, and therefore we just use our previous values to show log base 10p. So if log base 10p, so let's first of all let's find log base 10p. So we've got values for b. So so we can use ab to the power of t because we found b and we found a. Okay, so p is equal to 2 from a that we found in, my mistake, sorry, a is equal to 100. So a is equal to 100 and b is equal to 1.047. So P is equal to 100 times 1.047 to the power of 23. And therefore we substitute in our value. So 100 to the power of 1.047 to the power of 23 gives an answer of 287.59. So therefore 287.59 is much greater than 198. Therefore model not valid. So our model is much greater than the actual value. Suggest a reason for this one for not being valid. Essentially what happens is that it assumes that the relationship is the same. So you would just suggest any reason really. You could just say that the model incorrectly assumes that there is the same increase in squirrels year on year. Okay, or something to that effect would be perfectly fine. So just something along those lines is good enough. Okay, and then the last question that we've got is this one, part A. Question 8, or the fourth question we've got, is a simple model. The value of a car depends on its age, t in years. The following information is available for car A. Its value when new is 20,000. Its value after 1 year is 16,000. Use an exponential model to form for car A a possible value linking V with t. So this one, what we've got, so we want an exponential model. So we essentially we want V is equal to AE BT. Okay, so we want to find this sort of function. This is an exponential model, so it's got a constant at the front and then it's got t to the power of something, another constant. When the car is new, so when t equals 0, v equals 20,000. So therefore 20,000 is equal to AE to the power of 0. So A is equal to 20,000. Then the second one, t equals 1, where t is in years, so that means we just can put t is equal to 1. V is equal to 16,000. So here we're just going to say 16,000 is equal to 20,000 e to the power of b, because t is equal to 1. Then from here we just rearrange, so 16,000 divided by 20,000 is equal to e to the b, and therefore b is equal to ln 16,000 divided by 20,000, which is equal to, on the calculator, is equal to minus 0.2231. So your model is going to be V is equal to 20,000 e to the minus 2.2231 to the power of t. And that's for part A. Okay, the value of the car is monitored over a 10-year period. Its value after 10 years is 2,000. So here we're just going to use our model here to determine it. So V is equal to 20,000, so this is part B, 20,000 e to the minus 0.2231 times 10, because t is equal to 10 years. From here we just plug in our value, so 20,000 e to the power of minus 0.2231 times 10 is equal to V is equal to 2,148.42. If we look back at our original value, the value is 2,000. The reliability in this model is fairly reliable because it's reasonably close. 2,148 and 2,000 is close, but not completely, but not exact. So just a comment along the lines of reasonably close to the value, but not perfect. I mean, it's not way out. It's in the same, the same sort of significant figures in terms of the same powers. So 2,000, it's only 148 away, so it's not too bad a model. But essentially, this case here, we find that it's a reasonable model. Okay, and then in part C, explain how you would adapt the equation found in A so that it could be used to model the value of the car B. Also, just to point out part B as well, the time range as well. We're getting a bigger time range here, so of course, it's not going to be a perfect model. So the fact that it still matches it reasonably well is quite a good indication. Part C, explain how you would adapt the question in part A so it could be used to model the value of car B, where car B has the same value but depreciates more slowly. So for this bit, you're going to change the value of B. Now, this one here, you might be thinking, well, how can I change it? How can I read it? So essentially, what you want to do is, we know what the value is, t equals 10. So what happens when you change the value of B? So if you increase the value of B to minus 0.3t, then you are going to get the following. So minus 0.3, you will get 995.74. So it's clearly not increasing B. So therefore, don't increase B. So if you choose, for example, then B equals minus 0.1, and you solved it, so V is equal to 20,000 e to the minus 0.1t, then in this case here, we are going to get a value that's much bigger. So V is 7,357.59 pounds. So we can see here that if we want to, you don't have to show this, but you can do is explain how you would change the equation. So for this one, you would decrease the value of B. In fact, no, well, you'd be careful, actually, no, you would increase the value of B because you've got a negative. So actually, you would increase the value of B. So be very careful here. So here, when B is minus 0.3, 0.1, when you're comparing it to the original one, which was minus 0.2 something, here you're actually increasing it. So you would increase the value of B, and that would be your answer. And that's all the questions. Have any questions, please let me know.